Hey, I'm Trevor Makes, and in my last video, we took a look at the CBM80 signature that allows a Commodore 64 program to take over the reset function of the computer. And I also built a circuit that allows you to bypass that signature and reset the computer normally. But one of the comments on the video was from somebody who said they were looking for a hard reset circuit to build into a cartridge expander board they were making. And that got me thinking about how I would really go about building this circuit if I were going to do it from scratch, rather than just copying a design that I found on the internet. Now, the problem with the circuit that I showed off in the last video was that it pulls the reset and EXROM lines low through a capacitor and just slowly releases them back high as the capacitor charges back up. And so you don't really get a clean transition on those lines. Rather, it just, at some point, it creeps up between the logic low and logic high levels, and somewhere roughly within the window of where the timing needs to be, the line will transition high. It's a little bit hand wavy and not quite as precise as I would like it to be. So in this video, we're going to pull out a logic analyzer and do a bit more of a deep dive into the exact timings of that reset circuit, and then take a look at how we can build a much better circuit using a microcontroller board like an Arduino. Okay, so what I'm going to do first is put together an auto start cartridge using this cartridge adapter that I've used in my previous videos. And what I have here is an EPROM that I already loaded up with the pop-ups example from the previous video. So I'll just go ahead and socket this in here. Now, to make this work as an auto start cartridge, we need to have the EXROM line tied to ground. There's already a jumper there for that. And we also need to tie the ROM-L signal to the EPROM's chip select, which you'd normally do with a jumper like this. But because I want to hook the logic analyzer in here, instead what I'm going to do is use these two jumper wires. Put them there, one on the ROM-L and one on the chip select. And I'm going to plug them into the breadboard over here, like so. I just plugged them into the same row, so these will be connected. And I'm going to run the brown wire from the logic analyzer onto that same row. So that'll let us monitor the ROM-L signal. And likewise, I'm going to plug the reset into the breadboard along with the white line from the logic analyzer so we can watch the reset line. Okay, that's plugged in. And last thing, I need to plug the ground from the logic analyzer into ground somewhere. I'll just grab it off of these two headers. Okay. Okay, and so this cartridge is ready to go, so I'll go ahead and plug it in to the Commodore 64. There we go. And give it a power up. And there we go. Now, the pop-ups demo doesn't fully work because I have some of the variables actually stored where ROM is now, but it doesn't really affect how the timing works, so we're just going to go ahead with it. So I'll start capturing a logic analyzer trace, press the reset button, and there we go. Okay, so let's go ahead and take a look at this trace that we just captured. We have our reset pulse here, and we've got kind of this big dead space right here. This is actually going to be the memory test that the operating system does. We'll talk about that in a minute. But the interesting parts are going to be this little bit right after the reset and this little bit right after the memory test. So let's go ahead and take a look at this bit after the reset. First, we have to zoom in quite a bit. And shortly after the reset, about 30 microseconds after, we see these 5 evenly spaced ROM accesses. This is going to be that CBM80 signature check, which in this case is actually going to be read from the cartridge ROM. In this case, again, since that signature is found, it's going to continue to read the start location from the ROM and start executing code there. This first bit of code here initializes the timer chip and the sound chip, followed by another subroutine call here. This is going to call the memory test. Now, the memory test, we have to zoom quite a ways out again. Quite a ways out. Quite a ways out. Okay, there we go. What this does is it starts testing the memory from the video memory up to either the cartridge ROM or the basic ROM, whichever it encounters first, which is about location 1024 to, in this case, since it's hitting the cartridge ROM, 32,768, which is going to be just over 30,000 memory locations. Each of those takes about 50 processor cycles, which adds up to quite a bit of time here. Now, if we zoom into right at the end of the memory test, this first read right here, this is going to be where it reads the current value from the ROM. This second pulse right here is where it's going to write, attempt to write to the ROM anyway. Technically, this pulse right here isn't actually a write. It's the way the indirect indexed instruction work. It does a read right before it does a write. But the computer knows that it can't write to the ROM, so that write actually falls through to the RAM instead. And this third pulse right here, this is where it tries to read back that value it just wrote, but obviously it's going to read the same value as it originally did, not the one that it just wrote, which is going to end the memory test. So the takeaway here is we basically want to pull EXROM low within about 80 microseconds. As long as the EXROM line gets pulled low by this fifth read right here, that should stop it from reading the final byte from RAM in case the signature is present in RAM. And that way it will read junk and it should cause that signature check to fail. Then where it's much more generous on the timing is during this RAM test right here. We just want to make sure that that EXROM line goes high before the memory test reaches that cartridge ROM. We actually want that memory test to continue all the way up to the start of the basic ROM. Otherwise, the free basic bytes is going to read about 30,000 instead of 38,000. So now that we have an idea of what to do, let's go ahead and switch over to the Arduino IDE and start writing some code. First thing I'm going to do is define constants for the Arduino pins that I'm using. And first I'll do the two input pins. I need one for the reset and I need one for the ROM L line. Both of these are going to be inputs and I want to use the pin interrupts for these. And on an Arduino Uno, those pin interrupts have to be on pins 2 and 3. So I went ahead and assigned those like so. And the third pin we need is the EXROM line. This one's going to be an output, so I can put it anywhere. But I'll go ahead and put it on 4 just to keep the pattern going. Now in the setup function, we'll call pin mode to set up the reset pin as an input. Do the same thing for the ROM L line. Now those are both inputs. Now, as I mentioned previously, I wanted to use the pin interrupts for these. So we have to call the attach interrupt function. The first argument here, we need an interrupt number. So we call digital pin to interrupt with the reset pin here. Then it takes a callback function. I'll just call this start EXROM for now, followed by a mode. This is going to be the edge of the pin to call that function on. I'm going to use the rising edge and copy that for the ROM L. Do the same thing here, but I'm going to call this function end EXROM. Now down here we can create those functions, start EXROM and end EXROM. So what's going to happen here is when the microcontroller sees the reset line transition from low to high, it will automatically call this start EXROM function and execute whatever code we put in here. Likewise, it'll do the same thing with the ROM low line. When it does a low to high transition, it'll call this end EXROM function. And so the idea here is that when the reset line is pulled low, we want to also pull the EXROM line low. And then we just hold that EXROM line low until we see a transition on the ROM low line. And that's where we're going to release that EXROM line back high. So what we need to do next is just set up these two functions here, start EXROM and end EXROM. Let's start with this one. We'll call pin mode EXROM, make this an output, and digital write EXROM low. So that will just pull the EXROM line low. Now in end EXROM, here I'm setting the pin mode as an input just to release the pin. We don't actually need to drive it high since there are already pull-up resistors inside the computer that will pull that line back up. Now to finish off the setup function, we need to define an initial state for that EXROM line. So I'll just call this end EXROM here. And so that'll just make sure that the EXROM line is initially floating, not being pulled down low. Finally, the loop here, we don't actually need to do anything in loop. I'm just going to leave it blank since all the logic's basically being handled by these two interrupts. And so that's it for the code. It's, as you can tell, it's quite simple. Actually, it's a little bit of overkill for an Arduino Uno. If I were building this into an actual product or something, or installing it inside of a Commodore 64, I would not use an Arduino board like this. What I would actually use is a bare microcontroller chip, maybe something like an ATtiny4, just a little 6-pin microcontroller chip. But anyway, let's go ahead and get this program to the Arduino and hook it up to the Commodore 64. Okay, so we'll have to take the EPROM out and do that real carefully. I left it loose so it would slide right out like that. And I'm going to leave the ROM low and chip enables connected like they were, but we do need to take the EXROM jumper out here since we need to hook that up to the Arduino and also to the logic analyzer. There we go. So I'll go ahead and hook a ground up to that header along with the EXROM. Like so. I'll set that down. I'll plug the ground into the ground rail on the breadboard. And I'll connect that EXROM line to a new row on the breadboard over here. Like so. Now to get 5 volts for the microcontroller, I'm going to plug it in to the chip socket. So that's the 28th pin of the EPROM. That's a 5 volt line. And I'll just plug that right into the breadboard power rail. So we've got power and ground on the rail over here that we can tap into. And so I'm going to use the 3rd channel, the red line of the logic analyzer. Put a little jumper in there, and we'll wire that up to the EXROM on this row of the breadboard here. Okay, so now we have the breadboard set up. So let's bring the Arduino over here, hook up the 5 volts. There's the 5 volts. Let's run the ground. Okay, I got power and ground. And so lastly, we hook up the digital pins on the Arduino. We're going to do digital pin 2 to the reset line. Digital pin 3 goes to ROM L, which is this row right here. And finally, digital pin 4 will go to EXROM. Okay, there we go. Okay, let's go ahead and load up the pop-ups demo. And run. There we go. So the pop-ups demo is loaded up. I'm going to go ahead and start capturing a trace and then hit the reset button. There we go, and it worked. Okay, Now, the next thing to point out is that the signature is actually still present in RAM. So if we hit run stop restore, notice we immediately go back into the pop-ups demo. So I'll go ahead and kill that again. Now, if we want to get rid of it completely, what we need to do is instead poke at 32,772, and we can poke in anything really. I'm going to do a 0. And so that's going to get rid of the C in the CBM80 signature. So now if we do a run stop restore again, now we don't go back into the pop-ups demo anymore. Anyway, let's go ahead and take a closer look at that logic analyzer trace that we just captured. Okay, so this trace is a lot simpler than the one we looked at before. We can see the reset pulse right here, followed by the microcontroller pulling the EXROM line low, followed by that first read from the ROM low, looking for the 0 of the CBM80 signature, and the microcontroller following that read from the ROM releases EXROM back high. Because it would have likely read junk here instead of 0, it failed the signature check and continued on with the rest of the kernel code. The memory test would be going on until somewhere around here, that 2-second mark. But because we released the EXROM line already, there's not going to be any concern about the memory test reading the wrong value. And so, yeah, the microcontroller is doing its job perfectly, so I would call this a success. Anyway, that's it for this video. If you enjoyed it, please give a like, subscribe, all that YouTube stuff. Check out one of these other videos here. Thanks for watching, and I'll see you next time.